Dear friends and colleagues, good day. First of all, I would like to thank the conference organizers of Virtual Conference on Chemistry and its Applications, Research and Innovation in Chemical Sciences, paving the way forward, for giving me opportunity to present my work. Title of my work: Green Method for the Synthesis of Activated Carbon from Acacia Seed Pods impregnated with H3PO4 for removal of organic compounds from wastewater. Authors: Ateeq, Rahman, Hamushembe student, Manze Vuyaloa student, and other co-authors. This presentation is dedicated in the memory of Prof F P Kavishe, former Pro Vice Chancellor, Research and Development from University of Namibia. Outline of my presentation: abstract, introduction, motivation of study, objectives, methodology, production of activated carbon, AC, water treatment using the produced activated carbon, characterization of activated carbon, results and discussion, conclusion, acknowledgement and references. Abstract: acacia seed pods have been used for the synthesis of AC with H3PO4, that is phosphoric acid, as activating agent. So AC was obtained in three different particle sizes of 50 AC1, 100 and AC2 and 200 AC3 microns. So AC was characterized by scanning electron microscope, Langmuir adsorption, pH, moisture content, bulk density. So adsorption studies were conducted for methylene blue, methyl orange, phenol, ibuprofen drug, which is soluble in methanol, from aqueous solution with activated carbon obtained from acacia seed pods were studied at room temperature 25 degrees centigrade minus plus 1. So about 31% solids were adsorbed from treated water samples, while iron desorbed from AC surface into water. AC 1 and 2 and 3 showed higher R2 values when adsorption. Studies of methylene blue from Frenlet adsorption model were studied. 3 then Langmuir model. Though BET surface area was obtained around 617 and 164 for samples AC 1, 2 and 3 correspondingly, and the iodine number result was 528, 638, 553 for AC 1, 2 and 3. From these three samples of AC, however, the highest iodine number for AC2 was 638 plus minus 3.1 compared to AC1 and 2 and 3. These results reveal that prepared AC from Acacia aereleva is used for the treatment of contaminated water, which was characterized by UV. It is concluded that green method have been developed for the synthesis of AC from acacia aereleva for treatment of wastewater. Introduction. Acacia aereleva is also known as giraffe thorn or as camel thorn. It is an African species in the large taxonomical controversial Acacia genus. Some species of Acacia genus has been used by some Namibian companies in the production of charcoal that has been used for purification of water. Acacia seed pods are believed to produce high quality charcoal formed by slow burning, producing little ash. Activated carbons can be produced from any carbonaceous solid precursor, synthetic or natural. Activated carbons, they are solid, porous, black carbonaceous material. Activated carbon. The type of raw material used to produce strongly affecting its adsorption properties. Mainly it depends on the porosity. So porosity is a measure of the open spaces that are within the AC and this is characterized by surface area, that is BET, pore volume, ash content, and many physical properties can be studied. Preparation conditions such as activation temperature and time and chemical agents strongly they influence the porosity of activated carbons. Water utilizes utilities select activated carbons based on their characteristics, mainly depends on the porosity. So ACs that are employed in water treatment are commonly produced from coconut shells, which are mainly found in India in the southern part, that is Kerala, and even from other materials also it can be produced, that is date seeds, and pista shells, and any other shells which are hard carbonaceous material, bark of a plant, wood of a plant. So nowadays AC is being produced from various waste materials, that is mimicking the conditions used to produce AC from the commonly used raw materials, that is coconut shells. How adsorption of contaminants on AC works. So this is the figure 1 of the adsorption process by AC, how it is working. You have the carbon matrix, which is black one, there arrow pointed, and you have the small and large organic pores, organic molecules in that. Pores available to both the small and large molecules to get adsorption there, and pores available only to small molecules where they can be absorbed. So different pores are there for getting adsorbed of the small molecules for the adsorption, and you have the larger pores to get the large molecules for adsorption, because the contaminants can be large molecules or small molecules. So porosity determines the amount of contaminants to be removed from water or wastewater. It can be higher the porosity, the more contaminants that can be removed from water and or wastewater. So other factors such as water chemistry may influence the removal rate of contaminants from water, wastewater. So motivation of study. In Namibia, AC is used at various Namhwakaa and city of Windhoek water, that is wastewater treatment works, to control taste and odor that is causing compounds. The AC used by these utilities, it is purchased from abroad, mostly from Europe. They are procured. Since AC can be produced from low-cost waste materials, that is, acacia aerilova seed pods were selected in order to produce low-cost activated carbon. Acacia aerilova seed pods were selected based on their characteristics, that is, slow burning process and low ash content availability and accessibility. Objectives. The main objectives was to prepare AC using H3PO4 as impregnating reagent from acacia aerilova seed pods for removal of contaminants from water. The sub-objectives were to establish the produced AC's surface area, porosity, functional groups, moisture, and ash content. Establish the water treatment efficiency of the produced AC. To characterize the prepared AC from IR, BET surface area, Langmuir, and Fringlich adsorption isotherms. Methodology. Preparation of AC. Acacia aerilova seed pods were obtained from the campus of UNAM behind the Faculty of Science building. The material was dried, crushed, and seed pods were sieved to 50, 100 and 200 microns. Then when these were sieved through these microns, they were impregnated with 150 ml of 10% and 15% of H3PO4, that is phosphoric acid, and they were aged at room temperature for overnight. Next day it was filtered, washed with hot water, that is deionized water, 60 degrees centigrade it was, until the pH was neutral, because it has to remove whatever the materials are there in that after impregnating with H3PO4. So that once the pH is neutral, then it is dried in oven at 100 degrees centigrade for overnight. Then it is crushed with mortar and piston to powder. Then this sample is pyrolyzed in furnace from 500 to 550 degrees centigrade for 1 hour. Then once it is pyrolyzed in furnace, then again the samples are crushed in mortar and piston to powder if any lumps are there. Then these are washed with 0.1 mHCl in order to remove any impurities or ash formed. Then it is washed with warm water, 80 degrees centigrade hot water, in order to remove an acid and purify that. And the sample is again dried at 120 degrees centigrade in an oven for 1 hour. So this is the scheme flow chart for preparation of AC from acacia areloba seed pods. Then treatment of iron and gumms contaminated water. Weight 0.5 gram of each sample that received 50, 100 and 200 microns. Then pipette 150 ml of iron contaminated water. The mixture, then it is stirred using a magnetic stirrer plate for 2 hours 40 minutes at room temperature. Then gravity filtration is done using 70 mm Wattman filter paper. So this is the scheme 2 flow chart for treatment of iron and gumms contaminated water. Then characterization of the produced AC. Data analyzed here. Surface area is studied with methylene blue test. Percent ash and moisture. Density is determined. Then porosity with iodine test. Results: surface area studied, BET characterization is done, iodine number is evaluated, percent ash, scanning electron microscope studies is done for the morphology of the prepared AC from acacia seed pods, and moisture content. So this is the scheme 3, characterization of AC to determine its properties. Then results and discussion. Characteristics of the produced AC. That is, this is table 1. Percent yield, ash, moisture and pH of prepared AC. Moisture content AC1 for a 10% H3PO4 impregnated on AC, that is 23.24. 15% it is 23.44. For AC2, 10% H3PO4 impregnated and 15%, that is 21.62. 22.10. Then AC3 10% and 15%, 22.31, 21.88. Ash content obtained for AC1 10% H3PO4 impregnated 23.1, and for 15% H3PO4 AC it is 22.8. AC2 10% it is 22.8, 15% 23, AC3 24% ash content, 15% H3PO4 23. So volatile content is 21.5 for AC1 10%, 15% it is 22.01, AC2 22.85, 15% 22.5, AC3 22.5 and 15% 21. Percent fixed content 32.6 it is for AC1 10%, 15% 31.75, AC2 10% 32.73, 15% 32.19, AC3 10% 31 and 15% 31. Yield AC1 10% 76.97, 15% 76.8, AC2 10% 75.8, 15% 75.8, AC3 10% 78.8, 15% 78.9. pH AC1 10% 8.8, 15% 8.8, and AC2 10% 8.5, 15% 8.38, AC3 10% 8.5, 15% 8.7. Bulk density of prepared activated carbon. Table 2, bulk density of AC. So AC1, that is 10% with H3PO4, it gave 0.58, 15% 0.6, AC2 0.56, 15% 0.49, AC3 0.49, and 15% 0.53. So the bulk density of AC1, 15%, it is higher compared to other two, thus implying that is a better flowing consistency it has and packaging quantity of solid fuel material. Data of Langmuir and Fringlet adsorption isotherms. Table 3, data of Langmuir adsorption isotherms. You can see for AC1 50 microns and AC2 100 microns, AC3 200. So here the RT values obtained for AC1 50 microns is 0.312, and for 100 microns 0.948, and for 200 microns it is 0.726. So the better is the 100 microns AC2. Then data for the friendly adsorption isotherms for AC1 50 microns, 100 and 200. It is given here. You're getting 1.5 log C, 1.26 for the AC2, and AC3 1.2. So better is the AC1 here, and AC2 as well, giving good friendly adsorption values for both data of Langmuir and friendly adsorption isotherms. Then Langmuir and friendly adsorption isotherms, you can see for the iodine number of the produced PSC compared to PSCs produced in other studies, figure 2, Langmuir A and friendly B, linear plots for methylene blue MB, all this. So you can see linear AC1 and AC2 here. So it is more, whereas for the AC3 it is not much adsorption is there in both cases. Then Langmuir and friendly adsorption isotherms for methylene blue adsorbed on AC. So R2 values for the Langmuir AC1 50 microns, 10% is 0.85. AC1 for 50 microns, 15%, 0.83. Then AC2 for 100 microns, 10% and 15%. 100 microns, you can see R2 values have increased. So 100 microns is giving better result, 0.94. You have 0.938 and 0.94 only. And for AC2, 200 microns, 10%. And for AC2 200 microns, 15%. So R2 values are 0.6, 0.83. So a bit decreased for the AC2 200 microns, 10% is giving a little less result. So from this results, it's evident that the adsorption of methylene blue on AC was good from this adsorption studies of Langmuir and Fringlet adsorption isotherms. Then BET surface area of prepared AC compared with other studies here. Activated carbon prepared from acacia, areloba seed pods, H3PO4 impregnated. We have for the Langmuir, then BET we did not get. BET Langmuir, it was good. There the surface area for AC1A 620, then 615, then AC2A 547. Slowly decreased AC2. Maybe the pores may not be formed well for the AC2 with A and B, but whereas for AC3A and AC3B it is giving 600. Then activated carbon prepared from acacia seed pods with 5 reference with sulfuric acid. This is one. They got AC1 617, AC2 it decreased 62 only, AC3 164. So activated carbon from dumbstone, that is 200 to 250 microns, that is 957, very good, it gave in BET 512, reference 7. Then the activated carbon from date palm leaf lets, which is 1.19 to 0.25 mm AC. Langmuir didn't give much, and BET was 823. So surface area does not depend on the particle size, but the latter has influence on adsorbent and adsorption studies. Then characteristics of the produced AC EDX spectroscopy results lying near this. For the C, you can see AC1, AC2 are better results, whereas compared to the AC3 it was less. So water analysis results before treatment, that is Gamam's water analysis before treatment. pH is 7.5, which is excellent. Conductivity 221, which was excellent. TDS 12.4. Iron as iron 0.88 mg per liter, good result. Turbidity 4.3. NTO, it was good. Then UV analysis for iron contaminated water. You have the UV analysis for iron contaminated water with various prepared ACs. Blank water also has been done. So the results obtained from UV show that the absorbance is high at the lower wavelength. As the wavelength is increasing, the absorbance is decreasing. So water, you can say, straight line will come from the lower absorbance to the higher. And the orange one, we will see iron with 50 molar ACA. The absorbance was a little bit higher at low values, then slowly the absorbance decreased with increasing in wavelength. Same pattern is observed for iron 50 molar ACB, blue one. So there the absorbance at lower wavelength is high, 1.5 for the blue one. Then it slowly decreased from 350 as the wavelength is increasing. And same for iron 100 ACA, green one. Then the pink, you have iron 100 molar ACB sample. So this has at a lower wavelength higher absorption, or maybe 1.6 like that. So slowly it is, as the wavelength is increasing, absorbance is decreasing from 400. Then you have the iron 200 M green. Absorbance was low for this here. 200 microns was good one. ACA, that is absorbance was low there, from the low absorbance. Then as the wavelength is increasing, absorbance also decreased. Then for the iron last one, blue one, the absorbance was very high, 2.5. So it reduced very slowly for the 200 molar concentration of iron for ACB sample. So the absorbance, as the wavelength increased, the absorbance decreased from 500. So higher wavelength needed for that to decrease. So UV analysis of methylene blue of different concentrations they have analyzed, that is UV analysis for methylene blue with different concentration 1, 2, 3, 4, 5, 6 they have done. Then scanning electron microscope analysis of the produced AC. Here you can see the same images of prepared AC. A, that is 10% H3PO4, and B, 15% H3PO4 here. So external surface of the A is given. It is showing the rock types here, and if you see the B1 in that, internal when it is modified, taken one of the from the soft pictures, you can see the pores are formed there inside. Minute pores are there scattered on the internal surface. Then, and compared with the B1 15% A external, you can see the morphology, some rod types. Then, and B1, you can see how the pores are formed, scattered small pores which are spongy type. Then comparing with the C1 AC, which was prepared from acacia seed pods with H2SO4, and you can see A external, which is matching with the ACA 10% H3PO4, and AC B 15% H3PO4 impregnated on acacia. It's similar pictures. And the B1 is the internal image of that, which is showing many pores scattered in that. Soft pores are formed with H2SO4. This has been reported in Journal of Cleaner Production in 2019. So energy dispersed X-ray EDX spectroscopy results. Here you can see most of more than 90% we are getting carbon there, some amounts of calcium, oxygen, sodium, silica, alumina, copper is there, and with the B1 you can see in this only oxygen, silica, most of it is carbon. In conclusions, activated carbon was prepared from acacia seed pods, that is using H3PO4 as an activating agent. AC was produced from three different particle sizes ranging 50 for AC1, 100 for AC2 and 200 for AC3. So adsorption studies were studied for methylene blue, methyl orange phenol from aqueous solutions with activated carbon being prepared from acacia seed pods, which were conducted at room temperature 25 degrees centigrade plus minus 1 degree, and about 31% solids were being adsorbed, being treated from water samples, while iron got dissolved from AC into water. AC1 and 2 and 3, they showed higher R2 values when adsorption studies for methylene blue from friendly adsorption models were studied, 3 then Langmuir model. So however, the BET surface area was obtained to be around 617 and 62 and 164 for samples AC1, 2 and 3 correspondingly. And the iodine number result was 528, 638 and 553 for AC1, 2 and 3, and from these three samples surface area was represented well by friendly adsorption isotherms. So the highest iodine value was 672 mg for 200 microns particle size of AC. Iron on AC surface was adsorbed, reducing the iron concentration. So from all the characterization studies carried out, it is evident that activated carbon was prepared in the conditions stated above using H3PO4 as activating agent was well used and activated carbon was formed. So finally an environmentally friendly and economic approach was developed for preparation of AC produced from acacia seed pods. Acknowledgements. The authors would like to acknowledge the Faculty of Science at the University of Namibia, particularly the Department of Physics, Chemistry and Material Science for providing research facilities, and University of KWAZULU-NATAL for carrying out characterization studies of BET surface area and friendly adsorption isotherm, South Africa, for SEM and BET analysis. And finally, I dedicate this presentation to Prof Kavishe of PVC, who passed away recently. These are my references. Thank you. Any queries or questions are welcome.